Okay folks, let's see what we have learned so far. We're dealing with in graph theory and we're dealing with planar graphs. So we've learned about Euler's formula that says the number of vertices minus the number of edges plus the number of regions formed will always total 2. Well, the conditions here is that G must be connected, the graph. It must be a planar graph, meaning there are no edges that cross each other on that graph. There's V vertices, E edges and F regions. Okay, from that it followed on that if it's not a connected graph, what then? Well, then if it's still a plane graph, in other words there are no edges crossing each other, and there are CG connected parts, okay, connected graphs. There are a certain number of connected graphs. Then Euler's rule changes to 1 plus the number of connected graphs instead of 2. Okay, then we went on to the concept of maximal planar graphs. Those are just graphs that are planar with a maximum number of edges that graph can have while still being planar. Okay, so folks, let's see. The issue of triangulation came in here. So if G is a maximal planar graph with V vertices, where V is bigger and equal to 3, E edges, then E will be equal to 3 times the vertices minus 6. So this just tells us there's a number we can find, the number of edges, total number of edges that we have on this graph, by tripling the number of vertices and subtracting 6 from that total. From that came the corollary. Now what if it's not a maximal graph? Okay, so if G is just a planar graph with vertices bigger than 3 or bigger, so at least forming a triangle, and there's E edges, then the number of edges has an upper bound, and that is less than, or it can still be equal to, 3V minus 6. So this we call a bound. This is also a bound, and we're going to look at that now. Okay, so that comes from the following. It says, if G is a planar graph with vertices V and edges E, now notice that the vertices are not restricted to a minimum of 3. So in other words, there's no triangles. Here there were triangles. Then there's an upper bound on the number of edges, twice the number of vertices minus 4. Okay, we're going to prove that now. So let's see, how do we prove this lemma? We're going to start by saying, let us consider a plane graph G. So consider the plane graph or drawing G, and add, like we did before, edges such that there are no triangles formed. Okay, continue this to get the graph, we're still going to call it G prime, with E prime edges. Okay, so there's a different number of edges, and obviously the number of initial edges is less than equal to the number of new edges that we have added to this graph. Okay, so if we take the sum of all regions F of the new graph that we have formed, okay, we take the sum of the number of edges in each boundary of F. Okay, the number of edges in each boundary of F. What will we notice? Well, we don't want triangles, but there are still boundaries. to be formed. So we will have 4 times the number of regions, because each region will have 4 boundaries. But now remember, on this side here, we'll have twice the number of new edges that are counted, because some of these regions share a boundary line. Okay, so what do we notice? We notice that twice the number of new edges is now what? Is bigger or equal to the number of 4 times the number of regions. Now, why is that the case? Okay, because we have a situation where we had E edges, okay? We had E edges. So we've added edges. The number of edges are now bigger. Twice that number of edges are now bigger than what we had initially. Okay, so G prime has 4 edges on the boundary region, so that accounts for that number. And then the sum of all the edges on the boundaries have been double counted. Okay, so what do we see here? We see that F is smaller than or equal to a half E prime. That's the relationship we can find so far. Okay? But now what can we say? We can say that but G prime is a plane graph. Now, being a plane graph, what does that mean? It means V minus E plus F has to be 2. That's what Euler said the case is. Okay, so let's have a look. Therefore, 2 will equal the number of vertices did not change minus the number of new edges plus the F value that we have over here. Okay, so what does this tell us? Well, F is bigger than or equal to a half E prime. Okay, so hence I bring in F there is smaller than this. Okay, so it's actually F has got to be, this has got to face the other way around. There. Because F is smaller than or equal to that. Okay, I still have 2. I still have the initial number of vertices, and this is still the case. Okay, so let us see if I get rid of that fraction. I get 4 is smaller than or equal to twice the number of vertices minus 2E prime plus E prime. And if I now want to look at my number of edges that I have 4 2V minus E prime. So what am I going to do? I am going to throw the E prime over and bring the 4 to the right hand side. So therefore E prime is smaller than or equal to 2V minus 4. And that proves our lemma, that if the graph does not contain any triangles, then we can still say something. There is still a relationship between the number of edges and the number of vertices. It's just a bounded relationship. There's an upper bound. The number of edges cannot be more than, can be equal to, but cannot be more than twice the number of vertices minus 4. Okay, now we're going to keep that in our bank, and we are going to start answering the questions that they ask us in the book. I'm just going to fold this so that we have it at hand when we look at what the book is asking us to prove. Well, the first thing that your book asks us is to prove that K5 is not planar. Okay, so let's have a look. K5 is not planar. Okay, what does K5 mean? It means it's a connected graph that has 5 vertices, a complete connected graph here. So what does it look like? It looks like this. It's a pentagon where each vertex is joined with every single other vertex. So that goes there, that goes there, this goes here, that goes there, and that goes there. That's the graph of K5. Okay, that's what it looks like. So let's see. It has 5 vertices. How many edges? 1, 2, 3, 4, 5, 6, 7, 8, 9 edges. Let's just count again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 edges. Okay, and that's all we wanted, because we want the relationship between vertices and edges. Is this a planar graph? It's not. Okay, so G is definitely not planar. But what can we say? It has how many vertices? It has 5 vertices and 10 edges. Okay. Is it planar? Well, to answer that question, we have to answer, can we move things around here so that they do not cross? Can we redraw this graph so that it does not cross? Okay, so let's assume, let's prove this by proving a contradiction. Okay? Let's assume that K5 is indeed planar. Okay, if it's a planar graph, then we know that E, it's a planar graph, and there are triangles in this one. So we know that this is definitely true. 3v minus 6. Okay, because that goes for a planar graph with v vertices where v is bigger than 3 and e edges. This is true. Comes from the maximal planar graph theorem. Okay, now let's see. The number of edges we have is 10. So the number of edges will be less than 3 times the number of vertices minus 6. That means it's equal to 15 minus 9, and 15 minus 9 is 6. Okay, and in this case, 15 minus 6, what am I saying? 15 minus 6 is indeed 9. Okay, so the number of edges has to be less than 9, but there's 10 edges. Now, this is a contradiction. This is a contradiction. So, K5 cannot be planar. Okay, we used that argument quite well to prove that it's not planar. Okay, so let us look at the next proof that they want. They want us to prove the following. They want to prove that K3 is not planar. That's our next proof that we're going to look into. Okay, so let's remember the K3 graph means it's a bipartite graph with 2 sets of vertices. It's a connected graph with 2 sets of vertices, a complete graph. So let's draw that graph and let's see what it looks like. Remind ourselves. So every vertex joins with, every other vertex. So there we go, 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 and there we go. There's your bipartite graph. This is a bipartite graph. Okay, so how many vertices does it have? It has 6 vertices. How many edges does it have? Well, there's 9 edges in total. Okay, so we need to look at that and we need to see what it means. So there's 6 vertices, 9 edges, and it's a bipartite graph. So there is no odd cycles. It's bipartite, which means there are no odd cycles in this graph. Okay, so let's have a look. Since it has no odd cycles, means there's no triangles in this graph. Okay, now I think you can see it quite clearly. There's no triangles. Had there been adjacencies, then there would have been triangles in this graph. So what can we say? We go to the lemma where there are no triangles. So the number of edges has to be less than twice the number of vertices minus 4, if this is indeed the case. Okay, so what are we going to say? We're going to assume, we're going to suppose that G is planar. We have to, before we can use this. Okay? So we're going to suppose that K33 is planar, and then prove if it is the case, this is true. If this is not true, it can't be planar. Okay, so what can we say? The number of edges must be smaller than twice the number of vertices minus 4. So that gives us 12 minus 4, which is indeed 8. But there's 9 vertices. This tells us that it must be smaller or equal to 8. Okay? Which is a contradiction, since we have 9 vertices. Therefore, K33, the bipartite graph K33, is not a planar graph. Okay, there we go. We've shown both of those by showing that there's indeed a contradiction if we do have those, or if we assume that those graphs are planar. What did we base our proofs on, folks? Is our 5 theoretical approaches or theoretical things that we've proven. We've proven the lemmas, we've proven the theorems, we've proved Euler's formula, and we worked and proved with the corollary. Okay, now be sure that you know those. Those are not all in your book. So make sure that you take notes of these and that you know them and use them appropriately in your work. Okay, folks, we continue our discussion on planar graphs by looking at the idea of a polyhedron. Okay, polyhedra is a plural for polyhedron. A cube is an example of a convex polyhedron. Now you know what a cube looks like. It's like a little box. It contains 6 identical squares for its faces. It has 8 vertices and 12 edges. The cube is a regular polyhedron, also known as a platonic solid, because each face is an identical regular polygon, and each vertex join an equal number of faces. Okay, so let's see more about a polyhedron. Polyhedron is a geometric solid made up of flat polygon faces joined at the edges and at their vertices. We are especially interested in convex polyhedra, which means that any line segment connecting 2 points on the interior of the polyhedron must be entirely contained inside the polyhedron. Okay, so what do they mean? There's a little subscript at the bottom of our page. It says, an alternative definition for convex is that the internal angle formed by any 2 faces must be less than 180. Now folks, notice here, We have 8 vertices, 12 edges, and 6 faces, or 6 regions in the polyhedron. If we apply Euler's formula, it still applies. Okay, so the polyhedron, Euler's formula applies to the polyhedron. Now another way to draw a cube is represented over here. Okay, there's 1, 2, 3, 4, 5, 6, 7, 8 vertices, 1, 2, 3, 4, 5, 6 regions, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 edges. Okay, so if we work through the formula, we will see that in fact every convex polyhedron can be projected in a plane, and it behaves like what Euler's formula is saying it should behave like. Okay, what I want to do next is I want to look at the things that they ask us to prove in the book. Before we get to the example, let's just have a look at what they say here. We can apply what we know about graphs, in particular planar graphs. So where's our little arsenal of theorems? There we go. We can apply this to convex polyhedra. Since every convex polyhedron can be represented by a planar graph, we see that Euler's formula for planar graphs holds for all convex polyhedra as well. Okay, so let us have a look at the very first example. The first example is asking us, is there any convex polyhedron that consists of 3 triangles and 6 pentagons? Okay, so is there, that's the first question, is there any convex polyhedron that consists of 3 triangles and 6 pentagons? Now pentagon, what? 1, 2, 3, 4, 5. There. Okay, it's got 5 vertices each. Now remember, if we have a convex polyhedron, means it's a lot. These shapes are put together to form a new solid. Okay, so what are we going to look for, or what are we going to remind ourselves? Well, this thing here, let me use another color. This here has what? 9 edges, because it's 3 triangles. So there's 9 edges in here. How many edges are there in there? Well, where does a 9 come from? It comes from 3 times 3. Okay. Here we have 6 times 5. So here we will have 30 edges. Okay, now remember, all these edges are counted twice. Okay, so what does this mean? The total number of edges are counted twice. Okay, so to find the actual number of edges, we've got to take the 30, add it to the 9 and halve it. Now that gives us 39 divided by 2. Oopsie. If that was 38 divided by 2, that would be fine. You agree? So 39 divided by 2 is not an integer. Okay, so we can't have half a side in a convex polyhedron. So definitely there's no polyhedron that consists of 3 triangles and 6 triangles, 3 triangles and 6 pentagons. Let's look at the second part. What about 3 triangles? So the second one is asking for 3 triangles. And what about 3 triangles, 6 pentagons and 5 heptagons? 6 pentagons, and I'm not going to draw the next one, and let's say, what did they say, 5 heptagons. Now a heptagon is a polygon with 7 sides. Okay, so again we are faced with something that we don't know whether it exists or not. So here we have a total of 9 edges. Here we'll still have a total of 30 edges, and here we'll have a total of 35 edges. Okay, so if we add them, remember they double counted. Okay, so what is 35 plus 30 plus 9? If I halve that, I get 74 divided by 2, which is 37. Okay, that looks nice. Okay, so there's an integer number of edges that we have. Okay, now we've got to look at more than just the number of edges. Here we could stop at the previous one because the number of edges were not an integer. Here we end up with something that has a good number of edges, or an allowable number of edges. So that's the number of edges. So eventually we're going to look at the fact that we're asking ourselves, is V minus E plus F equal to 2? So we've got a legal amount of edges. Okay, so now the number of regions. So we're going to zoom in on the faces. Well, there's 3 triangles. So F will be 3 plus the 6 plus the 5 that they've given us here. There's 5 heptagons. So that we can see is 9 plus 5. 9 plus 5 is 14. Okay, so there's 14 faces. Now we've got to check our number of vertices. Okay, so our number of vertices is minus the number of edges plus the number of regions or faces, in this case is 2. Therefore, the number of vertices will be 2. The number of edges goes over, so I add 37 and I subtract the 14 from that. I get the number of vertices to be 25. Each vertex here has a degree of a minimum, or at least 3, because the smallest figure is a triangle in this case. So every vertex must have a minimum degree of 3. Now folks, if we look at this, okay, then each vertex so the vertices, the degree of the vertices is bigger or equal to 3. Okay, so the sum of the degree of the vertices is at least something. So the sum of the degree of the vertices is at least 3 times 25. Now this at least we could have replaced with bigger and equal to sign, because that means can't be less than that. So at least means it's more, equal to, or more. So this will give us the sum of the degree of the vertices will be bigger and equal to 75. So we've got all that information here. Okay, so now our argument. But the sum of the degrees must be at least twice the number of the edges. The sum of the degrees of the vertices must be at least, so it must be bigger and equal to, twice the number of edges that we have in our figure. So we've got 75. the number of edges is 37. So it's got to be more than that. Okay? So if we look carefully, twice the number of edges, there are strictly more than 37 edges. Okay? And there's 75. The sum of the degree of the vertices is 75. So let's look at that again. What are we saying? We're saying the sum of the degrees must be at least twice the number of the edges. Okay, why? Because there's 2 vertices per edge. Okay, so if we stick to this, each edge, there's 37 edges. So based on 37 edges, we need to have, what is 37 times by 2? We need to have 37 times by 2, which is 60, and 14, which is 74 vertices. Okay, so we need 74 vertices. We have a minimum of 75 vertices. Okay, so that's a problem. If we need 74 vertices and we have a minimum of 75, that is problematic. Okay, but we have 75 vertices. So that concludes that there is no such a polyhedron that consists of 3 triangles, 6 pentagons, and 5 heptagons. Okay, let's quickly talk about the second proof again. It's quite important that you understand it. Okay, so we've counted our number of edges, came to an integer value, we could proceed. Okay, then we needed the number of faces. Now the number of faces are given by the sum of those things. That's all there is to it. Now we can find the number of vertices based on our information that we have. We found that the number of vertices to be 25. Okay, what does that mean? The degree of each of the vertices must be bigger and equal to 3. Now that's the degree of the vertex is determined by the number of sides or edges that meet in that vertex. Okay, because our smallest figure is a triangle. So if we work with that, then the degree of the vertices, the sum of the degree of all the vertices, has a minimum value of 75. Then based on the fact that we had 37 edges, it means we can only have 74 vertices, because each edge has 2 vertices connected to it. The sum of the degree says it must be bigger than 75, which is not the case here. So there is no such a polygon that exists, because we can only allow for 74 vertices, but we have 75 of those vertices given to us. Okay, so let's have a look at the last, in fact, you know what? I will look at the last theorem that we're going to prove in our planar graphs, and that's the theorem that says there are exactly 5 regular polyhedra. There are exactly 5, so it means there's only 5, and not less and not more than that. Okay, we will look at that in our next video on planar graphs. Please like the video and subscribe to the channel, folks.